Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Quantum Well and Superlattice from the paper Physics at Nanoscale. So the learning objectives of this module are: we will be discussing about the quantum well and the superlattice. So students, let us start with a basic introduction about the module. A quantum well, students, can be considered as a potential well in which particle can have only discrete energy values, not continuous energy bands. Usually, quantum well, in the context of semiconductor heterostructure, demonstrates the confinement of a particle in one dimension potential profile. However, it is free to move in 2D. So, by forcing them to confine in a plane. So the effects of quantum confinement takes place when the quantum well thickness becomes comparable to the de Broglie wavelength of the carriers. It leads to the energy levels called energy subbands, that is, the carriers can have only discrete energy values. Now let us focus on AlX gallium 1-X arsenide to gallium arsenide heterojunction, which is a type first heterostructure. Now the conduction band offset between these materials is about 63% of the total band gap difference, which makes the valence band offset about when X is less than equal to 0.43. Now when AlX gallium 1-X arsenide layers are stacked alternately with different X, it is possible to fabricate the materials with unusual artificial band structures with novel properties. In fact, by alternating very thin layers of materials such as gallium arsenide, aluminium arsenide, one can construct a superlattice material which is unlike either of its constituent semiconductors. So both the conduction and valence band profile are the semiconductor analogy of the classic quantum mechanical problem of a particle in a one-dimensional box. So in this case, the conduction and the valence bands can be analyzed exactly as in elementary quantum mechanics. So the particle can be either a heavy or a light whole with effective mass as mHh star or mLh star, or an electron with the mass me star when the width of the potential well is sufficiently thin. So the particle inside it behaves quantum mechanically, that is, the particle exhibits discrete energy levels. So the semiconductor system is referred to as a one-dimensional quantum well. In the other two dimensions, the particle behaves semi-classically with a continuum of energy levels as dictated by the usual band structures. Quantum confined structures. That is a structure where an electron is confined in the material 1 and sandwiched between the materials 2 and 3. So as you can see from the figure on the left hand side, which shows the length of the quantum well to be as LQW, and the quantum confinement effect is delta Px approximately equal to h by delta x, and the energy of the confinement is approximated to delta Px square by 2m, approximated to h square by 2m delta x square. If E confinement, that is the energy of the confinement, is greater than 1 by 2 kT, so delta x is approximated to root of h cut square by m kT, approximated to lambda dEB, approximated to 5 nanometers. So this below figure shows the energy band diagrams for a quantum well, where the length of the quantum well is LQW, and this energy corresponds to EgQW, that is the energy difference between the edges of the E0E and E0H, and the length of the quantum well varies from 2 to 50 nanometers. So students, we can imagine a quantum well as a potential well in which a particle can have only discrete energy values. So as you can see in this figure, there is an electron in the potential V equal to 0, and outside the boundaries the potential is infinite. So usually quantum well in the context of semiconductor heterostructure demonstrates the confinement of a particle in one-dimensional potential profile. However, it is free to move in 2D by forcing them to confine in a plane. So here the energy in one-dimensional infinite potential well, it is quantized, and these are the energy levels corresponding to n equal to 1. We have E1, E2 corresponding to n equal to 2, and so on. And the energy is quantized, and the second figure shows the possible wave functions, that is, it is proportional to sine n pi x by a, and all the wave functions are being shown over here, that is psi 1, psi 2, psi 3, psi 4, and so on. And the probability distribution function for the electron, that is modulus of psi x the whole square. Quasi-two-dimensional system. So the energy band diagram for this kind of system is shown over here. That is, we have the valence band and the different valence band variations with K. First corresponds to the heavy hole band, second light hole band, third split off band, and the difference between the second and third shows or represents the split off energy. So the difference between the energy bands, the valence band and the conduction band, with the same K value, that is K equal to 0, gives us the direct band gap, and if the K value is shifted to some positive value, then we have the indirect band gap, and the band corresponds to the indirect conduction band. Now the figure on the right hand side shows the electron and hole wave states due to confinement in one dimension. LH denotes the light hole state and HH denotes the heavy hole state. So this figure shows the electron and hole wave functions of a 12 nanometer thick square quantum well formed with gallium arsenide and Al.2, gallium.8 arsenide. En denotes the nth electron state. LHN denotes the nth light hole state, and HHN denotes the nth heavy hole state. So, the energy eigenvalues of electrons and both types of holes, they are also plotted as a function of well thickness. The height of the quantum well is determined by the composition X of the alloy counterpart, AlX, gallium 1-X arsenide. The number of bound states in a single quantum well depends on the width of the quantum well. It is clear that it is possible to have different transitions either from the light hole or heavy hole states in a valence band to electron states in a conduction band. Finite well potential and graphical solution. So we have in this figure the finite potential well, that is the minimum value is 0 and the maximum value is V0, and the length varies from minus d/2 to plus d/2. The wave functions are also drawn over here for n equal to 1, n equal to 2 respectively. So the wave functions tunnel into the barrier and they are still identified by the parity and the number of nodes. The confinement energy reduced as compared to the infinite well and the graphical solution to find the value En. So consider we have an example of the gallium arsenide, aluminium gallium arsenide example, where the V0 is 0.3 electron volt, D is 10 nanometer, and this MW star equal to 0.067 ME, and MB is equal to 0.092 ME. So the A1 energy, that is for the finite potential well, the quantized energy for n equal to 1 found out to be 31.5 mega electron volt, and in the case of infinite well it comes out to be 57 MeV. Optical transition in a quantum well. So the left hand side figure shows a quantum well and the conduction band and the valence band, and the difference between the two is the energy band gap. Corresponding to the quantum well, we have the absorption variation for the h cut omega minus Eg in the units of h square by 8d square mu. So here absorption is proportional to the density of states, that is density of states constant in 2D, which is represented as G2D as a function of E is equal to m by pi h cut square. Thresholds: whenever h cut omega exceeds Eg plus En plus EHN, and the band edge, it shifts to Eg plus EE1 plus EHH1. Gallium arsenide quantum wells. Now we have the two cases over here for gallium arsenide, aluminium arsenide, multi-quantum wells having thickness D is equal to 7.6 nanometers, and the second one for 10 nanometers. The absorption spectra for the two is being shown over here, that is for n equal to 1 and n equal to 2, and the next one for bulk also it is given. So excitonic effects enhanced in quantum wells, which is strong at room temperature. So pure 2D, that is the Rx 2D, is equal to 4 multiplied by Rx 3D. So we have for a typical gallium arsenide quantum well, Rx is approximated to 10 MeV, which is approximated to 2.5 multiplied by Rx for bulk gallium arsenide. So there is a splitting of heavy and light hole transitions. So this figure, as you can see over here, shows how energy eigenvalues for electrons and light and heavy holes in conduction and valence bands of a square quantum well, which is formed with gallium arsenide and Al.2, gallium 0.8 arsenide are shown by this figure. So here En denotes the nth electron state, LHN denotes the nth light hole state, and HHN denotes the nth heavy hole state. So this figure shows the artificial band structures that can be created by growing the alternate layers of gallium arsenide and AlX gallium 1-X arsenide using different heteroepitaxial growth methods such as molecular beam epitaxy MBE or metal organic chemical vapor deposition MOCVD. So first A part corresponds to a square quantum well, second a parabolic well, C corresponds to a double barrier structure, the D part corresponds to an antisymmetric coupled quantum well, and lastly we have a superlattice. So this figure shows the several possibilities, that is by alternating very thin layers of materials such as gallium arsenide and aluminium arsenide, one can construct a superlattice material which is unlike either of its constituent semiconductors. So this shows the conduction band and valence band profile, where the semiconductor analogues of the classical quantum mechanical problem of a particle in one-dimensional box. So this figure shows the wave functions of the structure under the influence of the electric fields of various strengths. So it can be observed from this figure that either by an application of electric field or by varying the well width, it is possible to engineer the E1 and H2 wave functions. So when a moderate electric field is applied to the well, E1 and H2 wave functions overlap, which creates a strong absorption at a photon energy equal to E gap plus EH2 plus EE1. So as the absorption coefficient can be controlled by the strength of the applied electric field. So asymmetric coupled wells can be used for electro-absorptive modulation devices. So the properties of the single direct bandgap square quantum well can be engineered for light absorption and emission, and electron transport properties perpendicular and parallel to the epitaxial layers. Superlattice. A superlattice is a periodic structure of layers, typically of thickness of few nanometers, of two or more materials in one particular direction. So the two different semiconductor materials, they are deposited alternately on each other to form a periodic structure in the growth direction. So it is already discussed that quantum confinement leads to the observation of quantum size effects in isolated single heterostructure or double heterostructure known as quantum well. Now, if two quantum wells are grown on one another, there could be two situations depending on the thickness of separation layer between two quantum wells. If the thickness of the separation layer is less than the certain thickness, so that the eigenstates of the carriers in individual quantum well overlap substantially, so that the tunneling of the carrier from one quantum well to another quantum well. If the thickness of the separation layer is higher than the certain thickness Lb, then the overlap between the eigenstates of the carriers in individual quantum well will be negligible, resulting in the absence of tunneling of the carrier from one quantum well to another quantum well. So a periodic structure of the first type quantum well is called a superlattice, and the second type of quantum well is called as a multiple quantum well, which is shown in this figure. So this shows a periodic structure of layers, typically of thickness of few nanometers, of two or more materials in a particular direction. So depending on the thickness of the barrier Lb, periodic structure is called the multiple quantum well or superlattice. In the case of multiple quantum well, electron energies are discrete as in the single quantum well. In the case of superlattice, due to overlap of eigenstates, there are mini bands. So students, let us now discuss the types of heterostructure. Superlattice mini band structures depends on the heterostructure type, either type 1, type 2 or type 3. For type 1, the bottom of the conduction band and the top of the valence subband, they are formed in the same semiconductor layer. In type 2, the conduction and the valence subbands, they are staggered in both real and reciprocal space, so that electrons and holes, they are confined in different layers. In type 3, superlattices involves semi-metal material such as mercury telluride or cadmium telluride. So superlattice mini-band structures depend upon the heterostructure type, either type 1, type 2 or type 3. For type 1, the bottom of the conduction band, they are formed in the same semiconductor layer. So in a superlattice, the barrier thickness is very small, so the carriers can tunnel in the neighboring quantum wells due to significant wave function overlap between the adjacent layers. So this figure shows the formation of a band structure which is similar to the chronic penny model. In the superlattice, the bands are called as mini bands and the gaps, they are called as mini gaps. So this shows a band structure of a superlattice with a potential depth of 0.4 electron volt and a well barrier width W. Now the figure on the right hand side shows that the interband transition can be used to generate or detect the mid-infrared radiation around 10 micron. So students, let us summarize what we have learned in this module. First, we discussed about the quantum well, which is nothing but a potential well in which a particle can have only discrete energy values, which demonstrates the confinement of a particle in one dimension potential profile. However, it is free to move in 2D by forcing them to confine in a plane. Secondly, the artificial band structure that can be created by growing the alternate layers of gallium arsenide and AlX gallium 1-X arsenide using different heteroepitaxial growth methods such as MBE molecular beam epitaxy or metal organic chemical vapor deposition MOCVD like a square quantum well, a parabolic well, a double barrier structure, an anti-symmetric coupled quantum well and a superlattice was discussed. Next, the height of the quantum well can be determined by the composition X of the alloy counterpart, that is AlX, gallium 1-X arsenide. So the number of bound states in a single quantum well depends upon the width of the quantum well. Next, we discussed about the behavior of the wave functions of an anti-symmetric coupled quantum well, which can be modulated by applying the electric field. Lastly, we discussed the various types of heterostructures, that is type 1, type 2, depending upon the band structure, and a periodic structure of the first type quantum well is called as a superlattice and the second type of quantum well is called as the multiple quantum well. Thank you.